Good afternoon, class. Exam 2 review, Chapter 3, Differentiation Rules. Exam 2 covers from 3.1 to 3.8. Here's the last part, part 5, 3.7 to 3.8. 3.7, rates of change in the natural and social sciences. 3.8, exponential growth and decay. First, I'd like to look at an example in essence from the previous topic involving logs. We want to take the derivative of this expression y equals ln of 3x times x plus 4 to the fifth power. If we differentiate it just the way it is, that means you have to flip this over, write the reciprocal of this, and then differentiate this, which requires the use of the product rule as well as the extended power. Instead, we are going to decompose this. So the very first rule that we have here, I call it number 5, is the product rule. So ln of 3x plus ln of x plus 4 to the power of 5. So I'm going to do this in 2 steps. The first step is ln of 3x plus ln of x plus 4 to the power of 5. And then I use number 7, the power rule, and I put the 5 in front. And of course, ln of 3x, I write it as ln 3 plus ln x. So ln 3 is a number. The answer is 0. Ln x is 1 over x. We are going to differentiate the last piece, plus 5 times. Now we're going to flip this over. Here's the formula for natural log. Here's the formula for ln of g of x when we want to differentiate 1 over g of x. So 1 over x plus 4 times g prime by the chain rule. The derivative of x plus 4 is just 1. And so this is 1 over x, and this is 5 over x plus 4. And now, of course, the common denominator is x times x plus 4. So this is 1 times x plus 4. This is 5 times x. Basically, we get x plus 4 here. So we get 6x plus 4 in the numerator and stuff. So that's one of the topic we looked at previously, and now we are going to move. So a quick recap, decompose the log completely. And that's really a very important step. And then differentiate piece by piece. And section 3.7, rates of change, the difference quotient. As you recall, the difference quotient refers to basically rise over run when 2 points are given. Delta y over delta x, or f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. So you have 2 points, which, if you happen to have a curve, gives you a secant line. It's called the average rate of change of y, or f of x with respect to x, over the interval of x sub 1 to x sub 2, and can be interpreted as the slope of the secant line. We already know that. We recognize the following limit as being the derivative of f prime, okay? Again, reminding you of all of this that we have already discussed. And so, and this is the derivative at a specific point A. Okay, that's the definition. Limit of f of x minus f of a over x minus a as x approaches a, or limit of f of a plus h minus f of a over h as h approaches 0. Now, the average rate of change is the slope of this blue line or the secant line. The instantaneous rate of change is the slope of this red line or the tangent line. So m of tangent line is f prime of a. So there is really nothing brand new here. We are adding this concept and we are going to look at some applications. So first, we want to, given the constant, the cost function and the revenue function, we want to find each of the following: total profit. So again, C stands for the cost, R stands for the revenue. So we start doing some basic algebra and then we get into calculus part. So the profit function is very simple. By definition, profit is revenue minus cost. So you are going to subtract this from the cost. So you change this, each one of them, this becomes minus 62x squared, and this becomes minus 27,500. And basically, these two can combine into negative 74x squared. These two can combine to negative 27,490. Everything else remains unchanged. So the profit function is x cubed minus 74x squared plus 40x minus 27,490. Now let's find the total cost, revenue, and profit from the production and sale of 50 units. That means for the cost in here, replace the x with 50 for the revenue in here. And for the profit, we have two choices. One of them is in here, and I'll give you the second one in a moment. So first, C of 50, that means 62 times 50 squared plus 27,500. And you do the math. This is elementary algebra. So $182,500. So you do that. Revenue, plug it into this. What number? 50 units. So plug in 50 and evaluate that. So 50 cubed minus 1250 squared plus 440 times 50 plus 10. Again, use a calculator. Come up with the answer. So we get $97,010. What about the last piece, the profit? Well, we can plug it into here, which becomes 50 cubed minus 74 times 50 squared plus 40 times 50 minus 27,490. And you come up with the answer. You do the math. Or it's a lot easier, just say P of 50 is R of 50 minus C of 50. So subtract 182,500 from 97,000. And that gives you the same answer. Obviously, that's faster. There is no reason to calculate this. I just wanted to show you, yeah, plug in. But since the profit is revenue minus cost, it is always the case at any given point, whether it's 50 units or any other number makes no difference, everybody. Now, we are looking at the same question. We're going to continue with the question. We are looking for the marginal cost, revenue, and profit. That means marginal cost, marginal revenue, and marginal profit when 50 units are produced and sold. So marginal is an expression in business that refers to differentiation. So when we say marginal cost, that means find C prime. And if a number is given, plug in. If this number is not given, find the marginal cost. That means find C prime of X. So C prime of X is 62 times 2, 124X. So marginal means differentiate. Differentiate what? The cost function, the revenue function, and the profit function. So the next one is R, and of course you can plug in 50. That gives you C prime of 50. So 124 times 50. So this part, elementary algebra, we don't have to worry about that. I hope everybody is okay with that. R prime of X. 3x squared minus 24x plus 40. R prime of 50, replace the x with 50. So 3 times 50 squared minus 24 times 50 plus 40. And you put it into a calculator. It gives you 340 or $6,340. Again, P prime, I'm going to show you both ways. First, you find P prime. So you differentiate this, gives you 3x squared minus 74 times 2 minus 148x plus 40. Or you can subtract R prime from C prime, everybody. So this is also equal to R prime minus C prime. So if you do that, 3x squared remains, and minus 24x minus 124x becomes minus 148x plus 40, as you can see that. And so plug in 50, which means 3 times 50 squared minus 148 times 50 plus 40, and put it into a calculator. Or, of course, look at this one. You already have these two numbers, R prime of 50 and C prime of 50. So R prime of 50 minus C prime of 50. So it clearly gives you the same number, 140. Now, the meaning of it is extremely important. And here's the meaning of marginal, whether it's cost, revenue, or profit. It means the following. When 50 units, you have to pay attention to the number that is given to you. When 50 units have been made, the approximate cost of the next one, that means the 51st unit, will be $6,200. So C of 51st unit, how do you calculate? It's C of 51 minus C of 50, which that would be the precise answer. So what is this? Is that one? This is an approximation of that. How close is that? Let's just try this one. If you go to the cost function, plug in 51 minus plug in 50. Remember when we plug in 50, we already have the cost function from the previous page, $182,500. And so if you do C of 51 minus C of 50, the answer is actually 6262, $6,262. Now notice this number, how close it is to this number. Obviously, they are not identical, but the percent would be the difference between the two, which is 62 divided by original one, which is 6,200, which is very small. So about 1%. Okay. So the approximate cost of the 51st unit will be $6,200. That's the meaning of the marginal cost, everybody. And that is extremely important. Same thing for the revenue, same thing for the profit. So R prime of 50, this number, is the approximate revenue from the sale of the 51st unit will be $6,340. That's the meaning of R prime of 50. Now, again, if you want to calculate the exact amount, this is I can't emphasize this, this is an approximation. If you want the exact, find R of 51 minus R of 50. For an approximate profit on the 51st unit of P prime of 50, okay, which is $140. Okay. So I hope that's clear to everybody. The moment you see marginal, it refers to the derivative of that function, marginal cost, marginal revenue, marginal profit. And if you evaluate it at some point, in this case, we use number 50, then it gives us the approximation for the next unit, for the cost of the next product, producing the next unit, for revenue from the next unit, for profit for the next unit, for when we plug in. That's the meaning of that. Okay, let's move on, everybody. We are continuing with more applications. The distance in meters of an object from a starting point is given by S of t equals 2t squared minus 5t plus 40, where t is time in seconds. What is the velocity of the object from 2 to 4 seconds? Anytime 2 points in time is given, that means average velocity. So the average velocity is the total distance over total time. That means S of t sub 2 minus S of t sub 1 over t sub 2 minus 1. In this case, it's S of 4 minus S of 2 over 4 minus 2. That's the definition of average. Which means you're going to plug in 4 and then 2. 2 times 4 squared minus 5 times 4 plus 4d minus S of 2. 2 times 2 squared minus 5 times 2 plus 4d. That is the numerator, the denominator, obviously 4 minus 2. You do the math, this will become 52 minus 38. That is 14 halves or 7 meters per second. Let's do calculus. What is the instantaneous? What is the instantaneous velocity and acceleration of the object? What is the velocity and acceleration of the object after 6 seconds? To do so, as far as the velocity is concerned, you just take the derivative of the position function, the distance function. So v of t is s prime of t, which is 4t minus 5. And you plug in number 6, 4 times 6, 24 minus 5 is 19 meters per second. I want to make sure we understand the units and why this was given, as you can see, in meters. And this is the SDT. If you write it in Leibniz's notation, change in distance over change in time, meters per second. That's how you get your units, everybody. What about acceleration? Acceleration is the second derivative of the position function. A of t is v prime equals s double prime. So you take the derivative once, it gives you the velocity function, instantaneous velocity. And you take the derivative again, gives you the acceleration. So to take the derivative again, it just gives you a constant, 4. So the answer is 4, and that means it's independent of a t, and whether it's 6 seconds or 5 seconds or 2 seconds, this number doesn't change. But the units are meters per square second. Why is that? I want to quickly show you the reason for that. A of t is dv dt, the change in velocity, which is meters per second, over change in time, which is in seconds, and we get meters per square second. Just like the g-force, the gravitational force, which is 9.8 meter per square second. As far as the units are concerned, is the same as the g-force. When does the object reach a velocity of 31 meters per second? You go back to part B. Here's the velocity function. Set it equal to 31 and solve for t. When you move the 5, you get 36. You divide by 4, you get 9 seconds. Example 48. The height in inches of a sunflower X weeks after being planted can be approximated by the function f of x equals 6x minus 1/4 x squared. They don't have to mention that. You should know. Anytime you do application, you always give them back with proper units. Part A, how tall is the sunflower 8 weeks after planting? It's elementary algebra. That means plug in f of 8. So the first part, very straightforward. So we're going to replace the x with 8. So obviously this is 48, 64, 1/4 of 64 is 16, 48 minus 16 is 32, and the units, 32 inches. Find the average rate of growth from the end of week 6 to the end of week 12. Even if they don't mention average, when you have 2 points in time, that's what it means. And that means rise over run. That means delta y over delta x. In this case, f of x of 2 minus f of x of 1 over x of 2 minus x of 1, which is f of 12 minus f of 6 over 12 minus 6. That's the meaning of it, everybody. So the denominator is obviously 12 minus 6 is 6. F of 12, plug in 12, you get 6 times 12 minus 1/4 of 12 squared. F of 6, plug in 6, 6 times 6 minus 1/4 of 6 squared. 6 times 12 is 72. This is 144. 1/4 of it is 36. So 72 minus 36. This one is 36. So is this one. 1/4 of it is 9. So 36 minus 9. Actually, if you apply the negative, everybody, this becomes negative, this becomes positive, these three cancel each other. So we get 9 over 6 or 3 halves. Units, you pay attention to this one. Units of the numerator over the units of the denominator. Change in y, that means change in f of x, which is in inches, over change in x, which is time in weeks. So 3 halves of an inch per week. So on the average, from week 6 to 12, it grows that much on the average per week. Find the instantaneous rate of growth 10 weeks after planting. Now, even if they don't write instantaneous, if there is 1 point in time, that means instantaneous. So with that being the case, we have to differentiate. So we go back to the function f of x and differentiate. We write f prime of x equals 6 minus 1/4 times 2 becomes half of x. So minus 1/2 x. And because they said 10 weeks, you are going to plug in x equals 10. Obviously, this half of it is 5. 6 minus that is 1 inch per week. Again, the units, remember, f prime of x, that means df dx. Change in f over change in x. That's how you come up with the units. Very straightforward, and I hope everybody's comfortable with that. Explain the meaning of your answer. So what does it mean in part C? In fact, in part B, it means on the average. That means that doesn't mean that every week that was the growth, but rather on the average from 6 to 12, the increase was half of an inch per week. In this case, it's on week 10 or after week 10. On week 10, the sunflower is growing at a rate of 1 inch per week. We're going to continue with more application, 3.8 exponential growth. What I'm going over first, you are mostly familiar with the part that pertains to pre-calculus, college algebra, intermediate algebra. A quantity Q or Q of t, or Y of t, depending on the topic, you use different variables, is said to have an exponential growth or decay model if it increases or decreases at a rate that is proportional to the amount of the quantity present. A simple example would be the population, okay? So dy dt is ky, okay? If this, in essence, this is a differential equation, then y is c, some number, some constant, e to the power of kt, and that one is y of 0 or y sub 0, which makes that the initial value at time 0, the initial population, the initial investment, the initial size. Some of the formulas you are familiar with. If you recall, A equals P e to the power of RT represents the uh, investment, okay? Compound interest continuously. Or y equals y sub 0 e to the power of RT, or e to the power of KT. R or K are the same. Y equals C e to the power of KT. Q of T is Q sub 0 e to the power of KT. P is P sub 0 e to the power of RT. I'm showing you different formats you've seen depending on the context. We may use different variables. They all mean the same thing. For example, these two are identical. In this formula, A is the amount we end up with. In this case, capital P is the amount we end up with after so much time. Lowercase p here and uppercase P sub 0 here are the initial investment. R is the rate, T is the time. So C is the initial value. We talk about this one, of course. K or R, constant of proportionality is called, the relative growth rate. dp dt or dy dt, which is ky. dy dt is ky because y is the function. If we go with the p, everybody, then dp dt is kp. I want to make sure we understand these two formulas are identical. If you use y, you say dy dt, but if you use p, you say dp dt. If you use y, your function is y. If you use dp, then your function is p. Okay, in essence, you can think of it using this formula, okay, or this formula, okay? That's the difference. So when we use this one, we get this one. If we use this one, my point being, if we see slightly different variables, it doesn't mean the formulas are different. We're referring to the same formula. So conception is, the concept is important. So equation one, this one, is sometimes called the law of natural growth if k is positive, or the law of natural decay if k is negative. It is called a differential equation because it involves an unknown function y and its derivative dy dt. So that's the terminology. So in the case of exponential growth, dy dt is ky. In the case of exponential decay, dy dt is negative ky. And notice that y in both cases is the same, ce to the power of kt. So let's calculate actually dy dt. Let's differentiate everybody. So you see how we arrive at that. In other words, we will discuss differentiation, the solving differential equation later on in as of calculus 2. But over here, we gave you the answer. Let's say if we know this one, so it was this process is solving a differential equation. But if we don't know that, let's start from here and differentiate. So if I want to differentiate, what do I get? Dy dt is c, the constant doesn't change. And you are going to differentiate e to the power of kt, which is itself, because it's an exponential, times k. So one more time. How do you differentiate this? You keep the c, you keep the e to the power of kt, and you times it by k, the derivative of the exponent by the chain. And notice this part is y. So you have y times k, or ky. So when dy dt is ky, this is your differential equation. The solution to this differential equation is y equals c e to the power of kt. And we proved it actually by differentiating. Another differential equation is known as Newton's law of cooling. dt dt, the bad thing about this is that we are using the same. Capital T represents the temperature. Lowercase t represents the time, is a k capital T minus T sub s. So the dependent variable is capital T, the independent variable is lowercase t. The independent variable is time, and the dependent variable is temperature. So according to Newton's law of cooling, if you go through the process of solving it, you solve T of T and you get y sub 0 e to the power of kt plus T sub s, where y sub 0 is T sub 0 minus T sub s. T sub s is the surrounding temperature. T sub 0 is the initial temperature. And the difference between the two gives you y sub 0. Now, I'm going to look at some examples later on, and I'm going to make some sense out of this before we get to those examples. So I just wanted to give you the synopsis of the section first. So we will look at this later on. But for now, let's start with something that you're familiar with, nothing brand new, fairly simple. A population of bacteria grows from 1,000 to 4,000 in 3 hours. Assume exponential growth. That means you can use that formula. Find the population in 6 hours. So what is the process? So y of t is that, and the initial value is that. That means c is 1,000, or y of 0. Okay, y of 0 has 3 things mean the same thing here. C, or y at t equal to 0, or y sub 0. Please understand that if you set t equal to 0, you get e to the power of 0, which is 1. You see that? If t is 0, you get e to the power of 0, which is 1. So c, or y of 0, or y sub 0. So And then this one is y sub what? Y sub 3 is 4,000. This one, y at t equals 3 is 4,000. So let's write the given. So after you read the question, you want to make sure you understand what's given. And so you write down y of t has this formula. C is given as 1,000 and y of 3 is 4,000. You start with that. We want to find the population in 6 hours. So in order to do so, I highly recommend you always, and there are different methods. The best course of action is to find the formula first. And then by formula, I mean, we know C, we don't know K, so let's find K. So the process is to find K. Then we find Y of T in general, specifically for number 6. That is the process. So we're going to go in that order. So we're going to write, we know C is 1,000. It's given. And therefore, this formula becomes y of t equals 1,000 e to the power of kt. We also know y of 3 is 4,000. So if I replace the t with number 3, I get y of 3 equals 4,000 equals 1,000 e to the power of k times t, which is 3. So one more time, y of number 3 is 4,000. And in this formula, I'm going to replace the t with number 3. So obviously, I can divide by 1,000. That means just drop 3 zeros. So 4 becomes e to the power of 3k. How do I get to k? Take a natural log of both sides. ln of the left is equal to ln of the right. So k is ln of 4 divided by 3 because divide both sides by 3. Now, you want to be very careful here. I want to explain something here in a moment. So just pay attention, see what happens. When you are writing this, you really should, you have two choices. Keep it as ln 4 over 3, or just keep on going with more decimals. I'm going to show you the difference when you don't. So the formula for the function y of t is 1,000 e to the power of 0.4621t. So I stopped with 4 decimals. But notice what happens. Now I want it in 6 hours. I replace the t with number 6, and I multiply this by 6. I raise a to that power multiplied by 1000 and use a calculator, and I get this number. And because we are dealing with the number of bacteria, I go with a discrete value, okay, and I get 16,000. According, because the way you do the rounding, you want to round it to the nearest unit. 0 next to it is 1, so it remains at 0. So 16,000 is the answer. Now, what I want you to note first, note the following. From 1,000 to 4,000, it takes 3 hours. That means how many times more? 4 times. So in 6 hours, again, it should get 4 times. Why? Because 6 is 2 times 3. So every 3 hours, I mean, if you go with this, again, you might say, okay, there's an easier way I can figure it out, but we have to do math. It gets 4 times in 3 hours. So that means every 3 hours times 4. So whatever we have here, 3 hours later, times 4, 16,000. And this is the exact answer. Why didn't we come up with the exact answer here? What seems to be the problem? The problem is this, and I want you to pay attention to that. This wasn't exact. The more you carry the decimal, the better the approximation. So how do you make it exact? Don't change it. So what do you put here? If you keep this as ln4 over 3, then it will give you the exact answer, because e to the power of ln4 will be 4. Just so you can see what I am talking about right here. Right here, this one. Let me just erase the work first. This one, if you keep it as ln4, you get y equals 1000 e to the power of ln4 divided by 3 times t. And this is 1000 e to the power of ln4 times t over 3, and this part is 4, so it becomes 1000 times, so maybe you should put this one times 4 to the power of t over 6. And now when you plug in 6, okay, over 3, why this is 3, everybody. And if you put the t equals 6, that becomes 2. 1000 times 4 squared, you get precisely 16,000. In short, this will give you an exact answer. So if you're using decimals, use many, 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 many decimals. What we just did, everybody, was intermediate algebra, college algebra, whatever you may call it. Okay, so let's move on. Now, when will population reach 30,000, you set that equal to 30,000. You set this function equal to 30,000, okay? Obviously, you got to drop the 1,000 and this becomes 30. So in other words, drop 3 zeros here, three zeros here. You're dividing by 1,000. Now you're going to take a natural log of both sides. The reason you want to take a natural log of both sides because you're solving for the exponent, everybody. When you take the natural log, the right side becomes just that. If I put the ln for the right side, it just gives me the exponent 0.4621. So what is t? Divide both sides by 0.4621. Now this, you plug it into a calculator and it gives you about 7.3603 hours. And again, um, everything that you see here is an approximation, okay? So it takes about that much. And if you want to know 7 hours and how many minutes, so you multiply that by 60 because 1 hour is 62 minutes. Exponential decay. Physicists express the rate of decay in terms of half-life. The time required for half of any given quantity to decay. So before we get to this question, I want to remind you of some of this stuff. For example, we said y equals c e to the power of kt. If we go with this formula, the half-life h is minus ln2 over k, and k is minus ln2 over h, we can see the proof. I sort of show you, I remind you what you should have seen in previous courses. If you write it, in many cases, when it comes to exponential decay, they put the negative sign here. If the exponent contains the negative sign, y equals c e to the power minus kt, then half-life is just ln2 over k, which is really the same as doubling time as far as the formula is concerned. So normally, in many cases, they use m of t equals m sub 0 e to the power of kt. I'm showing you various formats that one may be represented, this format or this format, that ultimately means the same thing. This is the mass at time t. This is the initial mass times e to the power of kt. Now, a sample contains 1 gram of radium. How much radium will remain after 1,000 years? And they have given us the half-life for the radium, 1,620 years. Again, what does it mean? That means in about 1,620 years, it goes to half of the original size. In fact, you don't even have to know what is. 1, of course, becomes 0.5. But whatever the initial value is, so be it. Okay? You can use it as a C and then work on it. And that's, I'm going to show you, in fact, in a moment, but because I want to make sure that everybody is comfortable with the concept. So what is given in this situation? Y is c to the power of kt. If you decide to go with that formula, y of 0 or y sub 0 or lower or uppercase c equals 1, half-life is given as 1,620, and they want to know what is the amount after 1,000 years. So y of 1,000. So what we are writing here is what is given, everybody. So it's important to write the given first. So if we go with this formula and we want to look at the concept of a half-line, C represents the initial value. Half-line means the right side remains the same. This is half of the initial side, half of C. I want to make sure we understand why I'm changing the left side with half of C. C represents the initial value. We don't even have to know if it's 1 gram. Eventually, we can change it to 1 gram. But my point being, we don't even need to know how much the initial values, okay? But you keep it as c, it's 1/2. C equals c e to the power of k times t. Because the half-life is given, so you put the half-life t. If it wasn't given, you would say t and calculate in general. And you find the t in general, okay, as a function of everything else. So with that being the case, in order to solve for k, and by the way, the c from both sides, just drop them because they're identical. Now, how do you get to the exponent? You have to take a natural log of both sides. You take a natural log of 1/2, and you get the natural log of the right side. And of course, the right side, you put the 1620 in front of k. Please remember, k times 1620 is the same thing as 1620 times k. The difference is we should put it, and we do put it in front of it, okay? So the right side, you're taking the natural log of the e, and therefore you just get to the exponent 1620k. And the left side, ln of 1/2 is ln of 1. So this is 1620, the right side. And the left side is ln 1 minus ln 2, and ln 1 is 0. So minus ln 2. So k becomes minus ln 2 over 1620. Again, you can keep it as that because that's an exact answer. If you go with the calculator and do the approximation, you get, take a look at before actually we come up with the answer. K is minus ln 2 over h. In essence, we proved that, okay, everybody? And so now it's this number. Again, I'm approximating with the calculator, but this time notice 1, 2, 3, 4, 5, 6, 7 decimals. So that's pretty good. And so we write the formula. We go back here for this formula, everybody. For this formula, we replace the c with 1, k with this number. So y, and we write y of t, that's the meaning of it, is e to the power of negative 0.0004279 t. This shouldn't be there, class. Okay. And now this means replace the t with 1000. So you get e to the power of minus 0.0004279 times 1000. So it gets, the product of these two will get rid of these 3 zeros after the decimal. In other words, I mean, everybody knows that. The product of this gives us minus 0.4279. You put it into a calculator, and the answer is 0.652 grams. So after 1,000 years, we have 0.652 grams left. The growth in world population in millions is estimated by the formula P of t is 8,200 e to the power of 0.011 t, where t is the number of years since 2025. Find the instantaneous rate of change for the year 2050. Include units. Again, they don't have to mention include units. We must always. So Instantaneous rate, instantaneous rate, or even one point in time means differentiation. So you want p prime of t, you start with 8200, and then you differentiate this. That means you're going to write it itself. That's an exponential function. And you multiply it by the derivative of the exponent, which is simply the number in front of it, 0.011. So in essence, the derivative of e to the power of kx is e to the power of kx times k. That's what this number is. So 8200 was there already. So obviously, we're going to multiply these two first, and we get 90.2 e to the power of 0.011 t. In the year 2050, the difference is 25. So 2050 minus 2025 is 25. Replace the t with 25. It takes 25 years to get from 2025 to 2050. That's why the t is 25. So you replace it with 25. So 90.2. So p prime of 25, 90.2 e to the power of 0.011 times 25. You put it into a calculator, and it gives you 118.7511 million people per year. Please, class, here's how you come up with the units. This is dp, dt, the change in p, the population, over the change in t, time in year. So that's why we have the population, millions of people per year, which means in 2050, the world population will be increasing. Why increasing? Because this is positive. Otherwise, we would say decreasing at a rate of this much. Now, please understand, million has 6 zeros. So you move that means 10 to the power of 6. Let me just remind you. This means 10 to the power of 6, right? Or 1 with 6 zeros. So you move the decimal, how many places? 6 zeros to the right, you get 118,751,100 people per year. And we're done with that. I also want to remind you some information you should have. When y is c e to the power of kt and dy dt, of course, is ky, or dp dt is kp, k is, in this case, 0.011. Okay. This is the relative growth rate. Okay. K is the relative growth rate. And we want p prime of 25, which is, according to this formula, dp dt is k times p. So k times p, of course, at what point? 25. Please understand, this is dp, meaning what this formula really is dp as a function of t over dt equals k p as a function of t, and now t is 25. That's why p of 25, p prime of 25, kp 25. So k is this number, and p of 25, you put 25 into this. So 0.011, that's k, and p of 25, 8200, times e to the power 0.011, t is 25, and that will give you exactly the same. So this is another approach, because that's what they do in some text. I want to make sure to be clear on that. So what we looked at was the exponential growth and exponential decay, and you should be comfortable with that. We have seen it in intermediate algebra, college algebra, pre-calculus, and we also did the differentiation here. We added that layer. And now Newton's law of cooling, as we've already discussed, Newton's law of cooling has a specific formula I want to show you, and I want to go with this, reminding you when dy dt is ky, then y is c e to the power of kt, or y of 0 e to the power of kt. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding. Provided that this difference is not too large, this law also applies to warming. What are they saying? As you have a cup of coffee, a hot cup of coffee, and you bring it to the room, it starts cooling down. And if you keep it long enough, it has the same temperature. It will have the same temperature as the room temperature. On the other hand, you have a soda which is cold, freezing cold. You bring it to the room and it warms up until it gets to the room temperature. It follows the Newton's law of cooling unless the difference is huge. If we let capital T of T, remember, capital T represents the temperature, be the temperature of the object at time t, and T sub s be the temperature of the surroundings, then we can formulate Newton's law of cooling as a differential equation. dt dt, d capital T over d lowercase t is k times the parenthesis t minus T sub s, and again T sub s is the surrounding temperature. K is a constant. So I want to show you how we arrive at the answer. You're not responsible for it. If you can follow it, you are in good shape. So we write the formula. It really follows that because of the definition that it's proportional to the temperature difference. Please understand this one. Temperature difference between the object and its surrounding is this formula. Now, if we call this y of a t, if we give it the name y, then this is k times y, right? Or k times y of t. So we let y of t represent the difference between the t and t sub s. And remember, capital T is t of t. So let y of t be this parenthesis. This is by choice. Y is a function of time. Capital T temperature is a function of time minus T sub s. Let's differentiate both sides. When we differentiate, this becomes y prime, this becomes t prime, and this one is a number, class. Surrounding temperature is some number, some constant. The answer is 0. So this gives you y prime, this gives you t prime, this gives you 0 because it's a number. That means their derivative is the same. So y prime equals t prime. So we are going to write dy dt or y prime of t equals t prime of t or dt dt. So we proved they have the same derivative, everybody. So dy dt is dt or ky. So if that's the case, we know when we have dy dt equals ky, the answer is this. So for y of t, we have y sub 0 e to the power of kt. Please understand, I wrote it for you, capital C, or y of 0 or y sub 0. All of them refer to the initial value. If y of t is that, on the one hand, and on the other hand is t of t minus t sub s, that means t sub t minus t sub s is y sub 0 e to the power of kt. And if I move t sub s to the right, so these two are the same. If I move that to the right, I get capital T of t equals y sub 0 e to the power of kt minus t sub s goes to the other side, becomes plus t sub s. That's the proof of it, believe it or not. At t equal to 0. So let's both sides, let lowercase t be 0. So let's replace it with 0. When we do that, we get y sub 0 e to the power of 0 plus t sub s. As you know, e to the power of 0 is 1. So t of 0 is y sub 0 plus t sub s. So y sub 0 becomes t of 0. This is the same as t sub 0 minus t sub s. So I hope you can see that again. Let me write a couple of things for you to remind you. In this case, c equals y of 0 equals y sub 0. And in this case, t of 0 or t sub 0 refer to the initial temperature. At t equal to 0, what is the temperature? And so, as mentioned, t of capital T has this formula with y sub 0 being t sub 0 minus t sub s. So we proved the formula, and now we're going to look at a couple of applications. So as far as the Newton's law of cooling is concerned, you can use this formula again from the memory. Capital T of T, capital T represents the temperature as a function of time is y sub 0 e to the power of kt plus t sub s, where y sub 0 is t sub 0 minus t sub s. So as an example, we are going to look at a very basic example to get us started. A 180-degree turkey is removed from the oven and placed in a 74 degrees Fahrenheit room. After 15 minutes, it has cooled to 136 degrees Fahrenheit. Find the general solution for capital T. Whenever you come across this kind of problem, the Newton's law of cooling, find capital T of T first and then move on. So to find that, first write down what is given. This is the initial value. T of 0 or T sub 0 is 180 degrees. That's the initial temperature. The room temperature, as we bring it to the room becomes the surrounding. So T sub S, 74 degrees. After 15 minutes, T of 15 is 136 degrees. So this is the given. So take a look at what you do first. You read the question and you write the given. It makes it easy to finish the job. So one more time. The initial value, T of 0 or T sub 0 is 180 degrees Fahrenheit. The room temperature, the surrounding temperature, 74 degrees. After 15 minutes, T of 15 is 136 degrees Fahrenheit. Find the general solution. Well, we want to find this one. To find the solution, you need to find y sub 0, you need to find k, and you need to find t sub s. So I want to make sure we understand what we need to find. We need to find t sub s. Well, it's given. We need to find k. We're going to do that. We're going to need y sub 0, and to find y sub 0, we are going to use this formula y sub 0, because we have proved already y sub 0 is t sub 0 minus t sub s. T sub 0 is 180 and t sub s is 74, and therefore the difference is 106. So for this formula, we have everything except k. Let's write it. For this formula, we have everything except k. So t of t is y sub 0, which is 106, e to the power of kt plus t sub s, which is 74. So practically we are done. The only thing missing is k. How do you find k? This last piece of information. If you replace the lowercase t temperature, the time, with 15, the temperature becomes 136. And that will help us find the missing k. So t of 15 is 106 e to the power of k times 15 plus 74. So plug in. And what is that equal to? 136 degrees. So the very first thing, everybody, we are going to move this, make it minus 74, subtract it from 136, get 62, and write 106 e to the power 15k is 62. Divide by 106. Now, class, I can simplify this, but I don't want to do that. I want you to see where the numbers are coming from. At this point, anytime you have an exponential and you want to get to its exponent, you have to take a log. Because the base is e, we're going to take a natural log of both sides. So when you take the natural log of both sides, what happens? The left side just comes out, becomes 15k, because natural log and e cancel each other. So the left side is simply 15k, and the right side, just write it. So k is the right side divided by 15. Now use a calculator, and you end up with negative 0.035754. So T sub S, T of capital T of T has this formula, and now we have everything. So going back to this one, 106 T of T is 106 e to the power of kt, replace the k, plus 74. And that's the general solution. I hope you see it's not difficult, but it involves quite a few steps and logs and logarithmic properties that you should be fairly comfortable with. How long does it take for the turkey to cool to 110 degrees Fahrenheit? Well, T of T, this one, you set it equal to whatever the number is here, and you solve for it. Again, this is intermediate algebra, college algebra, you name it, pre-calculus problem. So it's really very straightforward. I hope everybody's okay with that. So what do we do? We move the 74 first, which means we subtract it with from 110, we get 36. We divide both sides by 106. Again, I'm not simplifying this, both divisible by 2. I'm not going to do that. I just want to continue with that. So you take a natural log of both sides, and the left side loses the natural log and the e, and it becomes simply the exponent. You divide the right side by negative 0.035754, and that gives you the t with a bunch of decimals you want to use. So 30.2, about 30.2 minutes, about 30 minutes. The reason you may change that, again, first you have to see if they ask you for an approximation and how many decimals. But aside from that, the whole thing is an approximation to begin with, okay? Where the cooling law, the Newton's law of cooling, is using approximation to a certain degree. But I hope you see that how much log and exponentials are involved here. You should get very comfortable with those. So these are some interesting applications. Let's look at another application. Put on your detective caps. How about that? A dead body was found at 1:30 a.m. when the temperature was 55 degrees Fahrenheit and the body temperature was 87 degrees. And reminding everybody that the normal body temperature is supposed to be 98.6 degrees. Nowadays, statistically, they have checked that it's slightly different, but let's stick with 98.6 degrees Fahrenheit. This is forensic, CSI in essence. This is how they figure out the time of death. So 1 hour later, so what they do, they wait for an hour on purpose. The body had cooled to 85 degrees, and so they measure it again. So originally they measure it, then 1 hour later, sometimes 2 hours later, and that gives them a chance to use Newton's law of cooling to figure out the time of death. And so of the three suspects, Goblin had an alibi for 10 p.m. and after. Mickey Mouse had an alibi between 7 and 10 p.m. And SpongeBob had an alibi until 12 p.m. Who has a good alibi? So what is the process? And that's what we are going to do. So this is an application we are going to do. This is what really happens in the real world. So it was found at 1:38 a.m. We're going to take this for t to be 0. At t equals 0, which means at 1:30 a.m., we measure the temperature, and the surrounding temperature is 55 degrees. You have to measure that. You have to check it. So this is the surrounding temperature. We measure the temperature for the body, and it's 87 degrees. So T of 0 or T sub 0 for the body is this one, 87 degrees. 1 hour later, you have a choice of say T of 1 or T of 60, whether you want to go with the minutes or hours is 85. So a quick recap. At 1:30 a.m., we're going to say T0. The temperature of 55 degrees gives us the surrounding temperature, T sub S. The body is at 87 degrees initially, right at that time. 1 hour, 60 minutes later, it's 85 degrees Fahrenheit. First, that's the given information. Now the question is, what do we do to find the answer? We are going to find the temperature at what time was 98.6 degrees according to all this given. We can calculate that, and that gives us the time. So let's get to work, everybody. Obviously, we are using the Newton's law of cooling. So we want to see what is given. T sub 0 is given. T sub S is given. So quickly, their difference, which is 32, 87 minus 55 is 32. That gives us Y sub 0. And if we put it into this formula, everybody, we say T of T is 32 e to the power of kt plus 55. We have everything except K. So K is missing. So we use this piece of information to find the value of K. So T of 60. So if I replace the T with 60, I should get 85. So T of 60 is 32 e to the power of K times 60 plus 55. I should get 85, which means obviously I'm going to solve it by moving 55 to the other side. This gives me 30. I'm going to divide by 32. Again, I'm not simplifying on purpose. I see e to the power of 60k. In order to get to the exponent, I'm going to take a log. Which log? The base is e. I take a natural log. The left side becomes 60k. And k is ln of 30 over 32 divided by 60 precisely. Putting it into a calculator gives us negative 0.001075. So we go back to this formula and everything is in order. K was the only missing variable. We replace it. So T of T, the general form for this situation is 32 e to the power of negative 0.001075 T plus 55. When was it supposed to be 98.6 degrees? We are going to set this equal to 98.6 degrees and find the missing time. So set this one equal to the normal body temperature, 98.6, and find the missing T. Of course, we're going to subtract 55 from both sides. We get 43.6. We divide both sides by 32. You take a natural log of both sides. Again, the reason we do so, because anytime you have exponential and you're going to get to the variable, which is the exponent, you have to take a natural log. The left side just loses ln and e because they undo each other, and we get to the exponent. So t would be the right side divided by negative 0.001075. You put it into a calculator, you get negative 287.7, let's say negative 288 minutes. What does it mean? According to this calculation, we said at time 0, we considered 1:30 a.m. to be time 0. So the death happened at time negative 288 minutes. Remember, 5 times 60 is 300. So almost 5 hours before that. Okay. So if you go 5 hours back, you get 8:30 p.m., but it's not 5 hours quiet. It's not quite 5 hours, so it becomes 8:42 p.m. And again, note 300 minutes equals 5 hours. 1:30 a.m. minus 5 hours is 8:30 p.m. So the reason we go with 8:42 because it wasn't 5 hours. So if it was, it's 8:30. That's an easy calculation. I want to make sure we understand where 288 is 300 minus 12. That's why you have 12 more minutes, 8:42. So about 8:30, about 8:42, the murder has happened. So who has a good alibi? Let's look at it. Mickey Mouse between 7 and 10 p.m. is in good shape. SpongeBob until 12 is in good shape. And Goblin had an alibi for 10 p.m. and after. What about before that? That's not good. And we know who did that. Goblin does not have a good alibi. That's what happens when you follow math. You can actually get to the proper answer. Fascinating.